In this video, I'm going to outline the engineering mechanics for Chapter 2 of the preliminary HSC for engineering studies. So this is part of engineering products, or engineered products, which is Chapter 2 of the Year 11 course. In the Coplanar textbook, this is under the chapter landscape products. That's the name that was called before the current syllabus. But this is the extent of mechanics, and especially the mathematical questions, that I set in the first assessment task for Year 11, which is what I call the mid-course review. Now, it doesn't look like much. When I talk about engineering mechanics, it's only one dot point over here, 2 dot points on the students learn to, and really all it's learning about is forces. But this is a fairly big and fairly difficult topic. I think this is the foundation of what we're going to learn, and I push to get to this point for the mid-course review because I want to establish for students, I want to see how well they have covered these concepts, so that way I can help people who don't do as well, because if we don't have this foundation as a solid foundation now, we're going to struggle for the rest of Year 11 for the next 6 months, and we're going to then struggle, well, very likely we're going to struggle for the remainder of the course. But it's a very long time until I get more formal assessment on these things. Okay, so the first thing we're going to outline is we're going to do a lesson where we're going to talk about the nature and types of forces. Well, to do this, we have to understand what a force is. So a very simple definition of a force, and I think this is the one that Copeland gives in his book, is that a force is a push or pull. I then add or twist. Most people give an answer, they say that force equals mass times acceleration. And that's very true, right? Force does equal mass times acceleration. But I find that you then get yourself in a cyclic argument to say, well, without defining it in terms of force being equal to mass times acceleration, what is a force? A force is something that causes an object to start or stop moving. But sometimes I could apply a force to a solid object, like a big boulder or a mountain, and I won't be able to shift that mountain because I don't have sufficient force to cause it to move. So in that case, we can say it's a push or a pull, and that's a very good definition. Well, I don't like it, but it's certainly a definition that I'm happy to give. Now, closely related to forces is strength, and you should be careful that whenever we talk about strength, we should never just say strength or stress. We should always talk about different kinds of stresses. And so I guess we could talk about different kinds of forces. We have tensile forces, which are pulling forces. We have compressive forces, which are squashing forces. We have twisting forces, which is called torsion. We have bending, and we have something called shear. Those last are a bit more complicated, but I might ask you to be able to identify certain examples. This is sort of a one-mark question. I might say, in the case of scissors, what kind of force is applying? And the answer to that would be shear. So we talked about that now. The next one is the addition of vectors. So the simple way of saying this is that if I was talking about someone hiking, and I said that they hiked at northeast for 2 kilometers, and then they hiked southeast for 1 kilometer. The resultant of that is, if I add those two together, is saying, well, how far is the hiker from where they started? So if this is where they started and this is where they finished, this here would be called the resultant. Often in this subject, we will be talking about things that are not moving. We might talk about things the second they're about to move, in which case we might have 3 forces acting on an object. And we might say, what is the force required to keep this thing still, to keep this thing in what we call equilibrium? Equilibrium means that all the forces acting on the object, including moment forces, which we'll cover in a second, are equal. So a good example of this, the classic example of this, is if we had a seesaw, and I told you that I had this seesaw here, and I wanted to find out if I said that I had a 30 kilogram kid sitting 30 kilogram kid, so 300 newtons in weight, sitting 1 meter away from the seesaw, and I had another kid, a larger kid, sitting half a meter from the seesaw, what would the weight of the larger kid need to be for that to be balanced? That's going to be, we're going to cover that in more detail, but the answer there is 600. Now, the same way here, we're going to have a third force that's going to keep this in equilibrium. If we just had those two forces, this thing would fall to the ground. But seesaws don't fall to the ground. What causes them to stay up is that there's a third force here pushing up called, this case, a reaction force. Looks odd when I write it that way. Is that spelled right? Anyway, I hope it's spelled right. A reaction force. Now, that's fairly simple, but when we start getting to bridges, I might tell you that I have a bridge, and on this bridge I have a force going sideways, and now I need to figure out what forces need to be applied to keep that in equilibrium. If it's in equilibrium, this force plus R1 and R2, I can say F plus R1 plus R2, they all have to equal 0. Way how we can write that is we can say the sum of all the forces, this is a sigma, I'm going to write that and make it really clear, sigma forces equals 0. We're going to cover that in a lot more detail, but the idea is that we need to prove that all the forces equal 0. Now, I'm going to take away my hiker for a second, and I'm going to say, well, in this case here, if I have three forces on the bridge, I have the stopping force of the truck, for instance, and I have this vertical force R2. That's a reaction force. And I have R1. Because this is equal, there's no missing leftover amount. The resultant of all these three forces, the resultant is equal to 0 because this is in equilibrium. That means all of these forces, when added together, equal 0, which means if we measure from where we started to where we finished, we're going to be back at the same spot. If we start here and go around this diagram, we're going to end at the same place. Okay, we're going to cover that in more detail, but it's good to sort of outline what we're going to do. So that's how we add vectors. Now, in a lot of these diagrams, I showed, for instance, earlier a bridge. Now, in my bridge, I said that there was a truck, and I said there was a reaction, and I said there was another reaction here. But the thing is, that's all I've drawn there are some arrows. What was actually here was there was a big stone arch with some bricks. And there was a big truck that was stopping suddenly. And underneath there was a person fishing. I don't need to draw any of that. That red diagram here, that red diagram, this drawing, or if I took a photo of this bridge, that wouldn't help me to solve what was going on. So when I strip everything away, we call that a free body diagram. The blue diagram that we have there that represents these forces, it's called a free body diagram. Okay. The red diagram is called a space diagram. The space diagram shows us more of a picture of what's going on, but we're not really interested in that very much. Okay, we've talked about resultants and equilibriums. I was a little bit ahead of myself there. Okay, the principle of transmissibility of forces, again, doesn't need a lot of detail. This concept is that if I have a wheelbarrow, that's my wheelbarrow. When we talk about a vector or a force, which is a vector, if I told you I was pulling on the, if I was mowing lawn and I was pulling it backwards, That's where I'd normally put the arrow to say, well, I'm pulling, that's the direction I'm coming from. But as long as this angle is the same, and as long as it's touching the same point, it doesn't really matter if I draw the arrow up to the left or the right. We call that the transmissibility of forces. It means that the force is the same whether it's to the left or the right of where we're coming from, as long as the angle is the same and the point of application is the same. We're going to talk more about that later, but that's the concept. It's fairly simple. It's not a question I'm likely to ask you in an exam. Okay, the next one is the three-force rule for equilibrium. Now, I have already recorded 5 or 6 videos from this. Almost no one likes to use this method. Most people would rather solve these things graphically. It's not worth talking about here. That said, if I've told you that it's something that could be in the exam, there's a very good chance that a question like this will be in the exam. And they're worth knowing. So I'm not going to go into detail now because I've already recorded so much on three-force method. Okay. The moments of a force represent the turning force on so we're familiar with the idea that if we have if I have my kid of mass of 300 Newton weight and my other kid of 600 Newton weight, I've said that there's a reaction force. What was the reaction? What's the size of the reaction force? In order to keep this in equilibrium, if I said all the forces are equal, what's the size of the force that needs to keep this equal? It needs to be 900 newtons. If it's not 900 newtons, the thing won't balance. It won't be balanced vertically. But the way that I could determine this was 600 newtons is to say that the amount that this beam is trying to turn is the same that this is trying to turn. That turning force, which is equal to the force times the distance, moment is equal to force times distance. I will talk about that, it's actually the perpendicular distance. I will talk more about that later, but for now, I mean, again, I've already recorded several lessons where I talk about moment forces. This is a very important part of the course. I'm so excited when I talk about this. I usually have 2 or 3 songs instead of my usual 1 song to talk about how excited I am to talk about moments. Okay, once we've learned about moments, we then have to learn about force couples. I don't really like force couples. They were one of the first videos I ever recorded. Generally, back in those days, if I recorded a video, it meant I didn't like something. And it just meant I've recorded this and now I never have to teach this again. The idea is that if I have a force here and a force here on a tap, well, the sum of the forces are equal, right? Because they balance. Let's say this is 200 newtons and this is 200 newtons. The sum of the forces vertically are equal, yeah? The top, this down balances the up, yeah, they're going to be equal. The problem is that what we're going to have is we're going to have a spin that's going to be created. A spin that's going to be created. So what that means is there needs to be another force, what we call a moment couple, that's going to prevent that spinning. Now, I recorded an entire video on this. I think it's pretty good. I might update it, but I've already made a very good video and I go into a lot of detail on moment couples. Chances of me including a moment couple question are low, but not 0. The last one is the equilibrium of concurrent coplanar forces. Okay, so the point they're saying here is, these are some complicated words, but we're going to break them down. Concurrent means that all of my forces meet up. So in the case of my bridge, where I have the truck driver stopping and these reactions, what we can find is that these forces all meet up in the same location. So how I draw that is I draw these red arrows. Could you give me the green pen, please? So what happens is I can draw these 2 forces here. They're concurrent, which means they meet up. And what I find here is this point where they meet up, which I call the point of concurrency. And once I have a point of concurrency, I know that this third force, if I have 3 forces, this is the 3-force rule, which I said I would describe later, but I wanted to talk about concurrent forces. If I have a third force, the third force must also pass through this point of concurrency. Once you have 4 forces, this rule doesn't apply. Or, It doesn't apply if the things are in equilibrium, but everything we do is in equilibrium, so don't worry about that. But if I have, remember we talked about in this earlier case, if I have the kid with 300 newtons and 600 newtons and 900 newtons, those forces, they don't meet up. Why don't they meet up? Because parallel lines don't meet. Parallel lines are non-concurrent. So when we talk about concurrent forces, the three-force rule only applies for when there's three forces and when they're concurrent and when they're in equilibrium. It needs three things to happen. It needs to be three forces, they need to be concurrent, and they need to be in equilibrium. Those three things need to happen for it to work. So when we talk about concurrent forces and non-concurrent forces, another way of saying are they parallel or non-parallel? Yeah, it's effectively the opposite term. Now, in terms of coplanar forces, the idea is that in the HSC, our forces have to all fit within a 2D space, a 2D plane. So what does that look like? Well, in the case of our bridge, all those forces, in the case of our bridge, and in the case, that's a terrible bridge, let me draw that. In the case of the bridge, and in the case of the seesaw, all of our forces are happening in the same 2D space. But there are many cases where it's not in the same 2D space. What do they look like? Well, if I have a stool, and someone sits on that stool, let's say I have a football player sit on the stool, and that's 1,000 newtons, I'm going to have four forces, go the opposite way, to balance those. What if, assuming those forces are balanced equally, what are those four forces going to be?
2,500.
They're going to be 250, 250, 250, 250. But do you see how those forces are not acting in the same 2D space? Those forces are acting in three 2D spaces, in three planes. Another example is if I have a crane being lifted, a crane lifting a box. Here's my box, and that box is being pulled on four cables. Those forces, they are concurrent. They're all passing through this same they all meet up at the same point, this point of concurrency. But they're concurrent, but they're not coplanar. They don't all fit in the same 2D space. These couldn't fit in the same slice. You can't fit all of those forces on the same slice of space. Okay, let's have a quickly look at the other side. Apply mathematical or graphical methods to solve problems. I will go through how to use both mathematical and graphical solutions to solve these things, but I will tell you that most people like mathematical methods better. Doesn't mean that they're right, but I like graphical methods, maybe I'm right. Okay, investigate and interpret the concept of equilibrium in the mechanics of engineered products. Okay, so equilibrium, I will talk about this at greater length. My saying I like to say is that for civil engineers, if it's moving, it's broken. Now that's obviously not true, right? Civil engineers design aqueducts that allow water to flow, pipes, they have moving water in them, and they're not broken. And there are obviously other examples. For mechanical engineers, they design planes and cars and things, and they move and they're not broken. But for civil engineers, if you're designing a bridge or a dam, if it's moving in any real sense, right, there might be some thermal expansion or something like that, or some seismic effects, but once it starts moving, that's generally not what we want to have happen. So the idea is that everything is still. Everything is, all the forces are equal, and that's what we want to have happen. So this is the concept. We'll go into a little bit more detail when we talk about equilibrium, but equilibrium can be summed up with these three important rules that are going to be the guiding factor, the guiding rules for most of the mechanics that we do for the rest of this subject. We know that the sum of the forces, I'm going to again write that as a beta sigma. This is the Greek letter sigma, which most of you have seen in maths. The sum of the forces equals 0, and the sum of the moment forces are also equal to 0. Now, we can draw the sum of the forces being equal to 0 by drawing a diagram, which you saw me do many times. but just earlier. But what we typically want to do is also, how we do it on computers, is we instead replace this rule with two smaller rules. We say the sum of the forces in the x direction and the sum of the forces in the y direction have to be equal to 0. And if we know that when we saw that seesaw, there were three forces, they were all vertical forces, we were easily able to identify what the missing force was. When we start having forces in two directions, it starts to get, when we have diagonals, it starts to get a little bit more difficult. And I'm going to show examples of how we can calculate what the equilibriants are or what the reactants, the resultants are when needed. But that's going to give you an idea. Now, when we do these calculations, we establish something as positive. That's what this first line means. These are the conventions that I will use for the rest of the course. Okay, that's my outline for mechanics for Prelim and Engineering Studies, Chapter 2.